Hello, everyone, and welcome to our virtual workshop on STEP into Kinematics and Newton's Laws of Motion. My name is Dr. Mary Urquhart. I'm an associate professor and head of the Department of Science and Mathematics Education at the University of Texas at Dallas, as well as director of our You Teach Dallas Secondary STEM Teacher Preparation Program. And with me today are teacher researchers, in particular, Suura of Coppell ISD, who has served as a project manager on this project while a student and has been instrumental in the creation of the STEP project. So what is STEP? Well, I'm happy to say STEP is a completely free web-based browser resource. So you can use it with your students to create simulations of common word problems that are already in your introductory physics curriculum, could also be used in middle school. There's absolutely no software to download. Again, it runs within a browser and it will work on common classroom computers, including Chromebooks. The only caveat with Chromebooks is you might have to clear the cache occasionally just because of the low memory within those devices. It may also work with tablets, however, it is designed to work with laptops or desktop computers. STEP was actually created through a National Science Foundation grant and by a large multidisciplinary team. So the leader of our team, Hagedorn Kiragawa, is from ATEC, or the Arts, Technology and Emerging Communications School, and has moved into science and mathematics education within my own department. We also have had a large team of students working on this project, and the coding for STEP was done by students. Now, our NSF grant has actually now ended, so STEP is being supported through the Department of Science and Mathematics Education because it is our intent to make STEP remain freely accessible to all of you. Our teacher researchers are also graduates of our Masters of Arts in Teaching program in Science Education. If you're interested in learning more about that program, or You Teach Dallas, which two of our teacher researchers who are also prepared to become teachers through, I encourage you to check out our QR code here. We are always looking for mentor teachers, particularly within high need schools near the University of Texas at Dallas. This presentation and its handouts are also available at the link shown on this slide, and we encourage you to share this with others. Now, our NSF grant was through STEM plus C, or STEM plus Computing for K-12 education. And the purpose of STEP was to infuse physics lessons with computational thinking through a scaffolded training environment for physics programming. So it's not programming as you may typically think of programming, in the sense that no specific computer language is being used or needs to be known in order to utilize STEP. So it has a low entry threshold. What we're really looking at is the overlap between the physics curriculum, so what you already have to teach, and then computational thinking. And in particular, aspects of computational thinking, such as modeling. In this case, when we're talking about modeling, we're meaning the type of modeling that you already do in your classroom when you do physics, as well as modeling in the sense of how you would solve physics problems with the assistance of a computer. We're also thinking about algorithmic thinking. So it's something that's critical, again, in both the physics curriculum and in the use of computing. And decomposition, yet another one of those overlap areas. So in the context of the physics curriculum, what we're really thinking about is taking those word problems, which can be such a challenge for students, regardless of the discipline, breaking those down into discrete parts that can be solved by both a human and a computer. And then that idea of abstraction and generalization. So being able to think about, for example, multiple representations of the type of motion that's being modeled in STEP, be the graphical equations or the physical motion that you'll see on the screen. So STEP has 3 different modules. Module 1 focuses on one-dimensional kinematics. Module 2 is two-dimensional kinematics. And module 3 is for Newton's laws of motion. These are the existing modules so far. We are seeking additional funding to create new modules and to keep STEPP up and running for all of you free of charge in the future. So this is the current public version of STEPP as of January 2022. When we envisioned STEPP, we thought about starting off with an unplugged activity. And part of this was to serve as an idea for teachers to figure out where students are with regard to their own concepts of motion in the very beginning of school, and then also to serve as a foundation for the type of modeling that we'll be doing in STEPP. So this is certainly not required, but we envisioned it as a way to help make STEPP more accessible to students. So in this activity, students are asked to work in groups to create their own concept maps of a car's motion using natural language. So we could use a toy car, a constant velocity car, some other kind of prop when we imagined this happening pre-pandemic in small groups within a physical classroom. Then what students do is they actually create those concept maps in their groups. This allows the teacher to actually take a look at what students' ideas are and the type of language that they're using. We imagine this for on-level introductory physics, again, within about that first week of school. So they may or may not be using more physics vocabulary. They could be using a lot of colloquial language in their representations of motion, or languages coming with them from middle school. And then the idea for module 0.5 is to actually do this with the teacher at the front of the room or with a video. We've actually provided a video for this. So using those ideas from concept maps for module 0, introducing this idea of a state diagram. So this is a computer science approach to modeling a system that's also called a finite state machine. So for example, in this particular version that we have here, you can see this motion of the car represented. And we have a state. This is a state of motion. So in this case, the car would be speeding up. And there's this transition then to another state. In this case, it has to do with time. So after 1 second, state 2, the car will be going at a constant speed. Then there's another type of transition between states, which in this case would be determined by distance. So after the car goes 1 meter, it will slow down. And then we have yet another transition with distance until 1.5 meters, and then this toy car would stop. Now, the videos that we created to help facilitate our own field test for module 0 and 0.5 are available here. We also have an entire suite of videos available on our website for the different modules to help provide introductions for you and your students. So here's what module 1 looks like. We start off with that natural language level. Again, you can go to any level you like, or just the ones that are of interest to you, or you can do them in order. It is scaffolded so that as you go from one level to another and one module to another, the inputs become more advanced, and I will show you that in a moment. So if we look at that in module 1, level 1, again, this is the natural language module, so we're not assuming that students know vocabulary, such as what acceleration means, that it can be both speeding up or slowing down, that it could also be a change in direction. So here, we're just using that colloquial language. So students would select from pre-built states. There's no need for them to worry about transitions. All that is taken care of for them. All they have to do is select new states, choose one, hit submit, go on to the next state, and then they can model the motion as it's happening for this car. So you got to get an idea of what that motion actually means. So then if we move past that first natural language module, students will be able to have their own inputs for these systems. They can name the state. You can choose whatever name you like. There is a character limit. For the very first level above the natural language level, so level 2, they would simply choose a position, and you can have an initial, a final, and a displacement. For the second one, we're actually introducing velocity and then moving on into introducing acceleration. So for module 2, we have, again, different levels, and just as before, how you would use that is completely up to you. With STEPP, we're not providing you a curriculum. We're providing you a resource that can be used to be integrated within your own curriculum. So Ken is going to take you through some problems for some of these modules and levels. However, those are just examples, and again, it's meant to be used with what you are already doing within your own curriculum. Here are some examples of those scaffolded inputs by module and level with module 2. And you can see they're a little bit more complex because we're dealing with two-dimensional motion in our module 2. But again, going through displacement, velocity, and acceleration. Now, as we move into module 3, we get a lot more variety in terms of the type of levels. But again, these are intended to be scaffolded. So you can go from one to another, or you can use only the ones that are of interest to you. How you use STEPP is completely up to you. This is showing you, again, some of those scaffolded inputs by module and level. And you can see now we're introducing mass and force. And that's net force. We have modules that have gravity built in by default, but you can also change the value of acceleration due to gravity. And then we have ones that are the vertical motion, has the gravity built in. The horizontal motion does not. You can add additional forces to any of these. You can also change what STEPP looks like and the features that you have displayed. So the customize option is really nice. You're able to turn on and off vectors. You can show the trails of objects, and they are color coded. I'll show you an example of that in a moment. You can change your backgrounds and characters. You can also determine what units you're going to be using within your STEPP simulation. You can show the equations as well. We've noticed in our early field testing with the women in physics campers, so those are mostly middle schoolers, they really enjoyed changing objects and backgrounds. That seems to be true with even the adult teachers that I have in my own physics class. So it really is something that's fun and enjoyable for students. And that was part of the design concept behind STEPP, was to use the Unity game design environment to provide something that was visually appealing and fun enough to be something students would want to interact with. So here's an example of one word problem. This one was from Ken, showing how STEPP can be used, showing again those color-coded states. So if you can see on that graph, you have the opportunity, by the way, to turn on and off graph displays. We've got our state 1 in blue showing on the graph. We have our state 2 in orange, then our state 3 in green, and then finally our state 4 in red. Now, one of the things I love about STEPP is that you see dynamic animation with those color-coded graphing and vectors added to it. So let me go ahead and show you what this looks like. Here we have a chicken. That chicken undergoing accelerated motion with two different states. Now, the reason why we have the option to turn on and off items such as vectors and graphs is to be able to reduce cognitive load when needed, but also to provide additional information when your students are ready for that. STEPP also has an assessment mode that hides the calculated numbers. This was something that was a request from our focus group of teachers, that one of the powerful things STEPP can do is actually do calculations. But if you're using it, let's say in the context of an exam, you won't want students to have that particular capability, but you still might want to use STEPP. So the assessment mode puts a nice bright red border around STEPP so that you could quickly walk around a classroom and determine which version of STEPP is being used. I invite you to go ahead and give STEPP a try. So here's our website, stepp.utdallas.edu. What you'll see when you go to this website now is Play Public version. Please select that if you'd like to go ahead and give STEPP a try. But before you actually go to this website, I recommend that you stay tuned for what Ken is about to present you. Ken has done a fantastic job as a project manager and as a student lead of the curriculum team. He actually created not only the video tutorials that you'll find on our website, but worked with students in the field tests that we conducted at the University of Texas at Dallas. He's created a lot of sample problems, and he's about to do a fantastic job guiding you through some of the capability of STEPP. Thank you very much for your attention, and I'm turning it over to Ken.
Thank you for that intro, Dr. Mary. Hi, everyone. My name is Ken. I am going to walk you through some of the levels and modules of STEPP, as well as some practice problems so you can have a better idea of how you might integrate STEPP into your classroom. So let's go ahead and dive right on into Module 1, which deals with one-dimensional kinematics. We are going to go into Level 1, which is for natural language. And so here's our animation area, and then below is our state diagram area. We can go ahead and add a state if we press the plus button right here. And if you click on the rectangle that shows up that says State 1, it opens up the state window, which is where all of our inputs for the state go. And so for this level, we can pick from a menu of pre-built states to describe the motion of the object. And so this is how we expect students to describe motion when they first walk into the classroom. And so we can just pick one state and hit submit. And we'll get a message from STEPP saying, great, ready to run. And that just means that STEPP is able to create an animation based on that input. It does not necessarily mean that it is the correct answer to the problem. And we can go ahead and press the plus button to add more states. You'll notice that the state is grayed out when you first add a state, and you can't play the animation either. You need to edit and submit the state. And you need a great ready to run message before you can run the state diagram. And you'll notice that the grayed out state changed color, so you should not have any grayed out states in your state diagram. You can delete states using the delete button, but you can only delete from right to left. So for previous states, you'll notice that the delete button is absent. If you'd like to completely start fresh and delete all of the states in your state diagram, you can press the clear button. You'll be prompted asking you if you're sure. And if you hit OK, it'll delete all of the states in your state diagram and you can start over. If you have a state diagram that you love and you feel like you want to submit this to an assignment on your learning portal like Canvas or Google Classroom, you can press the export button. It'll create a .fsm file. It'll show up in your downloads folder. Just a quick note though, if you have your browser settings such that it opens files that you've downloaded automatically, your computer will give you an error message telling you that you cannot open a .fsm file. And that's not an issue with the file. It's more so just that you don't have a program that can open a .fsm file because it's meant to run through the STEPP application on the browser. So you can just ignore that message, and then you can upload it onto Google Classroom or whatever you need to, or you can import it into STEPP using the import button. Pressing this, it'll create a pop-up below the application prompting you to choose a file. So if you press that button that says choose file, it'll open up your Windows Explorer or Finder if you're on a Mac to select that file, and it'll upload and propagate the state diagram area with that state diagram. Okay, so regarding practice problems, so here's a problem that I would envision being used for Module 1, Level 1. So draw a state diagram for the following scenario. A chicken begins speeding up to the left, then it moves at a constant speed in the same direction. it notices danger and immediately starts moving in the other direction at a constant rate for a little bit, and then slows down to a stop once it feels safe again. So you'll notice there aren't any numbers, there aren't any calculations involved in this problem. It's primarily focused on breaking down a word problem into chunks. And so we're focusing on that skill in this level. And so this can be a fun skill-based activity. It could be collaborative or gamified, where you have them write scenarios for each other and they try to create a state diagram as quick as they can. And so it could be a really fun activity for that. If we go ahead and create a state diagram for this, we look for keywords. So chicken begins speeding up to the left. Okay, we're starting off by speeding up to the left. So that sounds like move left, speeding up. Go ahead and press submit. We can add another state. So then it moves at a constant speed in the same direction. Okay, same direction. We are moving to the left and we're moving at a constant speed. Okay. Next one. It notices danger, okay, and immediately starts moving in the other direction at a constant rate. So now we're moving to the right at a constant rate, which is the same as a constant speed. And then lastly, slows down to a stop once it feels safe again. Okay, so we're slowing down to a stop. And then we can even customize our character. So we're chicken in this problem. And we can press play to watch the animation go. See how it's color-coded by state. And so we can see how the motion, what kind of motion we're doing in each state. And so that's our state diagram. We can export it, play again. We can watch it at 2 times speed, 4 times speed, half speed. We can reset and watch again and whatnot. And so that's some of the functionalities and how I would tackle this problem for Module 1, Level 1. Okay, and so, since this is a skill-based thing, you can spend as much or as little time as you see fit for this level. But it is a stepping stone as we move on to level 2, which deals with displacements in 1 dimension. And so you'll see that the interface doesn't really change much going between each level. The state window will change a little bit based on the inputs needed for each level. And so for this one, we can change the name of the state, we can set an initial position, and we're inputting a displacement. So we can put in like 10 meters. And you'll notice that once we hit submit, it automatically calculates and fills in this final position. If we're on the assessment mode, then this value will be hidden. And you'll notice that the final position for state 1 is the initial position for state 2. For that continuity, there's no teleportation in physics. If we want to go in the opposite direction, we're going to use a negative in our displacement. And we can keep adding states. Then we can press play to do our animation. It automatically does the transitions. We don't have to worry about that. If you don't want students to necessarily have to download the file and whatnot, and you'd rather them just submit a screenshot, then you can press the show all button and they can take a screenshot of this part right here. It shows all of the state inputs right here. We also have a graph that is drawn in real time. It is also color-coded. And so we can also hover over the graph to see specific values as well as the slope, because the slope of the graph is very important in physics. And so let's go ahead and look at a practice problem. You begin at your house. You drive 5 kilometers to the east to the library. You realize you forgot your phone at home and have to drive west back home. By the time you get back and you get your phone, it is time for the library to close for the day. You decide to drive west 8 kilometers to go to the mall. You shop and are invited to your friend's house. You drive 3 kilometers east until you get to your friend's house. Setting your house as your reference point, what is your final displacement? What distance did you drive? At which location was your displacement the largest in magnitude? At which location was your distance traveled the largest? So let's break this down. So we're driving 5 kilometers to the east. So let's go ahead and set this to kilometers. So we're driving 5 kilometers to the east, and we're starting at the reference point. Okay. So 5 kilometers to the east, to the library. You realize you forgot your home phone, and you have to drive home Okay, and so we go back 5 kilometers, so negative 5 kilometers. And then, okay, so this sentence doesn't help us. You decide to drive west 8 kilometers to go to the mall. So west, so that's negative 8. And then you shop and are invited to your friend's house. You drive 3 kilometers east until you get to your friend's house. So 3 kilometers to the east. Positive 3. And so we have our state diagram. And so then we can play our animation and see it go. I'm going to change this to 2 times speed just for sake of time. And see our animation play out. Okay, and so you can see just visually what our displacement would look like. So from here to here. You can also look at the initial and final positions on the state diagrams. You can add up all of your displacements. You can look at the graph as well and compare like this point to like this point and whatnot. And you can see that since it's color-coded, we can see graphically what the motion looks like as well. So connecting all of those representations of the motion all in one very versatile program. And so that's how I would tackle that problem and model it so that it can be a lot more visualized for the students. Okay, and so that's Module 1, Level 2. Again, if you want them to submit a screenshot, you can do that. All right, so we're gonna go ahead and change level. And so Module 1, Level 3 deals with velocities. So now we can set an initial time and an initial position. And we have a velocity for the state that we can like play around with. So it can be positive, negative, or 0. And then we also have to set a transition condition now. So when this state is going to end and move on to the next state. And so that can either be a final time or a final position. So we're traveling like 5 meters per second for 2 seconds. Or we're traveling 5 meters per second until we travel, have a displacement of 10 meters or something. Something like that. Press submit. And the other value, the other transition condition will be filled in for you. And then we can see that the initial conditions for the next state are the final conditions of the previous state. If you decide you want to change the transition condition for this state, you can press this triangle, which is meant to represent the transition between states. And you can change it to be, like, let's say we want it to be 15. And so we can change it so that it gets updated. Again, we can edit the next state. And again, our sign convention is positive to right, negative to the left. Once we're happy, we can press play. For our animation, we can click show all, take a screenshot and whatnot. But I'm going to look at this practice problem. Maria is driving down the street. She starts out driving 18 meters per second. After 15 seconds, she encounters a school zone and starts going 8 meters per second. Once a total time of 20 seconds has elapsed, Maria resumes at a speed of 20 meters per second until she has driven a total of 30 seconds. Okay, so we're going to create a state diagram for this. So first state, she's starting out driving 18 meters per second. So there wasn't an initial timer position specified, so just setting 0 is convenient. And so she's driving like that for 15 seconds. So 15 is our transition condition. Hit submit. Add a next state. Now we're going 8 meters per second until a total time of 20 seconds has passed. Okay. And then Maria resumes at a speed of 20 meters per second until she has driven a total of 30 seconds. Okay, and so that is our state diagram. And so we can go ahead and press play for the animation. Once again, I'm going to speed this up just for sake of time. And so we can look at the graphs. So graphs being drawn in real time. And so if we hover over, we can see that the slope of the displacement or position versus time graph is the actual value for the velocity in the velocity versus time graph. So our slope is 18, so our velocity at that time is 18 meters per second. Okay. It also draws the tangent line for you. Additionally, if we hover over the velocity versus time graph, we have the area under the curve being highlighted for you. If you want to hide that, you can hide, on the graph, you can hide the area under the curve. And that is Module 1, Level 3. So moving on to Module 1, Level 4, now we can define an acceleration. So again, this acceleration can be positive, negative, or 0 if you want to just demonstrate constant motion when the acceleration is 0. You specify an initial time, initial position, and an initial velocity. So we're really thinking about like VI, VF, or V0 if you use V0 for initial velocity, as well as the position and time. And for our transition condition, we can pick a final time, final position, or final velocity, one of those. And so we can accelerate from rest at a rate of 5 meters per second squared until we're moving at a velocity of 10 meters per second, something like that. And we can add another state. And so with the transition, you'll notice that we can add a kick. So this is if there's a problem where, you've kicked the object and now it's suddenly moving 10 meters per second in the opposite direction. And you want that velocity to be different in the next state compared to the previous state, just suddenly. And so that's how you can make that happen with the kick. And so then we can have, let's say we're slowing down to a stop with an acceleration of 2 meters per second squared. Okay. And so we can press play and watch that animation play out. One thing I didn't mention in the previous level that's available there is the velocity vector. As well, in this level, we've added the acceleration vector, so you can see the vector representation of the motion. So you can see the constant acceleration vector, but how the velocity vector is changing over time with the motion. And so that's another representation that's available. Okay, so I can look at a practice problem for this. So a driver is going east down a straight level road with an initial speed of 16 meters per second for 3 seconds. After noticing a yellow light, the driver presses the brakes such that the car has a uniform acceleration. The car stops right at the line before the intersection. If the magnitude of the car's acceleration was 4 meters per second squared, what distance did the car travel while it was slowing down to a stop? Okay, so let me clear the state diagram. So for the first state, I was traveling 16 meters per second, and I'm doing that for 3 seconds. And so I'm moving at a constant speed, so I can set my acceleration to 0 meters per second squared. And I'm doing this for 3 seconds. And then I'm slowing down to a stop with a constant acceleration with magnitude 4 meters per second squared. So since I'm slowing down and I'm initially moving in the positive direction, my acceleration is going to be in the negative direction. I'm slowing down to a stop. So that's a final 0 meters per second. So this is really useful for identifying what variables you're given, right? As well as thinking about, okay, what's the sign of my acceleration going to have to be? We can watch the animation play out. So constant motion, no acceleration vector. Now we're slowing down. We have an acceleration. My vector for my velocity is shrinking till I have reached a stop. So then I can look at the distance I traveled with my change in position right here, since I'm moving in a straight line. I can look at my graphs. So now I have a position versus time, velocity versus time, and an acceleration versus time graph. They're all vertically aligned with the same time scaling drawn in real time. So we can look at what's happening with the slope on each of these, the shape of these curves. And once again, we see that the slopes in the area under the curves, they match up beautifully between each of the graphs. And then for level 5, we're dealing with free fall in one dimension. And so it's vertical accelerated motion. So it's identical to the previous level, except now we are working vertically. And so a problem that I can imagine using for this one would be you throw a ball upwards at a speed of 5 meters per second, neglect the effects of air resistance, acceleration due to gravity has a magnitude of 9.8 meters per second squared. How long does it take for the ball to fall back down to its original height? And so on. So for this, I have an initial velocity of 5 meters per second, and my acceleration is going to be negative 9.8 meters per second squared. Okay, and it's very tempting to say, okay, I want to come back down to the original height, so then my final position would be 0 meters. But if I hit submit, you'll notice that the final time is 0, and the animation, if you play, it's instantly over, right? It's picking the solution where we're already at the final position, so we don't need to do anything. But that's not the answer we're looking for in our problem. Instead of using our final position of 0 meters or trying to calculate a final time, sure, you could do that and just use this to check your answer. Or you can be smart about it and realize, oh, well, if it's falling back down to its original height, it's had time to accelerate as it went up, and it's had the same amount of time to accelerate as it came back down with that symmetry, right? And so when it comes back down, its final velocity should be 5 meters per second downwards. It should have the same speed. And so when we do that, our animation works, and you notice that our final position matches our initial position. And then we can watch our animation. Again, we can show the vectors. Really useful for demonstrating that acceleration due to gravity is always minus 9.81 meters per second squared on Earth, near the Earth's surface. And that's how I would tackle a problem in Module 1, Level 5. And so that is Module 1, all of the levels in Module 1. As we move to Module 2, so you'll notice that we have a 2D grid. So we have a X and a Y. If we wanted to show a grid, we can. For a grid for the X and Y coordinates. And now instead of just position and displacement, we have our X and Y position as well as our X and Y displacements. You know, just think of it as a 2D version of something we've seen before. We can show our graphs, and so now we have graphs along X and graphs along Y. But again, this is just a 2D version of stuff we've seen before. Same with Module 2, Level 2. Instead of just time, position, and velocity, we have time, X and Y position, and X and Y velocity. Again, we have our graphs, which we have along X and Y. All right, for 2D accelerations, we have our time, position along X and Y, velocity along X and Y, and acceleration along X and Y. And so this is what you're going to use for your projectile motion problems, whether it be horizontally launched or angular launched problems. Just keep in mind, if you do an angular launched problem, you are going to have to use trig to break it down into X and Y components. Right? Again, we have our graphs along X and Y, as well as our vectors. We've had our vectors as well. All right, with level 4, 5, and 6, we start diving into circular motion, which, depending on what your scope and sequence looks like, this might be something you skip. This might and come back to later. This might be something you dive into right away. It really depends. But with level 4, we start with looking at circular motion with natural language, so we can look at different kinds of circles, different sizes, different directions, different speeds. And so we can look at that, and then we can look at the vectors and see how the vectors change. We can see our centripetal acceleration towards the surface as well as our perpendicular tangential velocity for our circular motion. And so you can really compare between these states to see how the vectors change. If you wanted to, you can look at the graphs, but that might be hit or miss depending on the level of physics you teach. With level 5, we start dealing with the actual inputs for circular motion. You'll notice that I'm only able to put in one state in our state diagram. And so this deals with polar coordinates, which might be hit or miss depending on what level of physics you teach. We can input our circulation speed, which is our translational speed, as well as our centripetal acceleration. We can move clockwise or counterclockwise and whatnot. And then with level 6, we're putting it all together. You can have one of those problems where you're moving on a circular track and then it gets released from that circular track. What happens? It could be a circular track on a flat table where it just goes along that inertial path straight forward, or it could be like a vertical circle and then you let go and you have that projectile motion. There are a lot of options there. For module 3, we deal with Newton's laws, so we start looking at mass. And so for this, we can look at during the transitions. Oops, forgot to set a final condition. We can see that I'm going to speed this up. The force is applied during the transitions because the states are constant motion. And then we can see the force vector during the transition and see the result. For level 3 and 4, dealing with forces, we can add forces. We can add the components, essentially. And we can just input like that and press play. We see the net force displayed on the state diagram object, and then we can open a free body diagram. So we can have the net force, and then we can have the separated forces all visualized on our free body diagram. Okay. And then we also have an inclined plane level where you can set an inclination degree and input the forces that are parallel and normal to the plane, setting friction if we want to. Circular motion along the idea of Newton's law. So instead of centripetal accelerations, we have force. We have centripetal force as well as mass. Okay, and then with Newton's third law, we have two objects. And when they meet at the same place at the same time, they will collide. And we can actually set elasticity for the collision if you're interested in that. So when you deal with momentum, you can always revisit this as kind of like a callback. And so you can set we can set the state diagrams for each object. And you'll notice that the time got changed because at 2 seconds, they'll be at the same time, same place. And so there will be a collision. If we play the animation, we see the objects are in a collision course. And boom, we have a collision. We see from the force vectors that they exert an equal and opposite force. And we see those forces on here. But you'll notice there's a different acceleration because the masses are different. And we can even look at the collision duration, which is especially useful when we get to impulse and momentum, but, you know, for Newton's third law just by itself, this part may not be useful. Okay. But that is Module 3, Level 7. Okay, and so that is Newton's laws and all of the different ways we can use STEP in the classroom for all different kinds of topics and activities. All right. And so hopefully that gave you a lot of insight and ideas of ways you can integrate STEP into your classroom. Hopefully got a bunch of ideas. Thank you so much for joining us today. I hope you enjoyed this presentation. Thank you all so much. Have a wonderful day. Bye-bye.